So now we are on the way of proving that number of classes is the same as number of irreducible representations. Theorem: reduction of any representation into irreducible representations is unique. The image we have about what irreducible representation is that, when we have kind of diagonalized everything maximally, the original big matrix representation of every group operation, finite number of these matrices, order of the group of them, they can all simultaneously be brought into block diagonal form where there are smaller blocks and zeros of the diagonal. So that's what we have in mind. And each one of them is a representation. They don't mix. So I can write. Now, a character for that thing is I just sum up things on diagonal, and it's a sum of characters for the subblocks. And that only depends on the class. So I can always write kth class. Its character, which is a sum of diagonal elements of the matrix representation of that class. This is kind of obvious because if all group elements, so all elements in the representation have been block diagonalized by what we have just done, then there is a block alpha, there is a block beta, and so on, right? And everything else is zero. So when I take a trace, I'll pick up character of first block, second, third, and they're by definition irreducible representation because we have done this as well as possibly can be done. So we have written it in terms of irreducible representation. And now this thing here could be that beta happens several times. These integers count how many times happens in this block diagonalization. We do this in the usual way. So these weird chi's, they're really components of vectors whose dimension is the number of classes. And we have orthonormality between them. So we will project various components using that. Look at our character orthonormality relationship. It says that conjugate of alpha class K times psi. And let's call this sum J. This is some number, right? This is integer number of classes. We're summing over classes. And these guys would be orthogonal were it not for these weights. So what I'm doing is I take my big representation, which is reducible, and compute its character. That's this thing. And then I project it onto individual irreps. And now I substitute in here this formula. This is supposed to give me some number, right? Because each one of them will be irrep. Irreps are all unitary vectors, and then there'll be some of these integers. So I get formula that is this integer, how many times the thing happens in this whole projection, dot, 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 alpha is. So this gives me the number of times irreducible representation shows up in my reducible representation. And that's all there's to it. now we can use this to count the number of irreducible representations. The theorem is number of irreps equals the number of classes. We had the character orthogonality theorem, and now what I'll do is I will take a square root of number of elements in the classes and absorb it into definition of this vector and its permission conjugate. So I can write it as always, it's a sum of the classes. Number of elements in a class divided by the group character evaluated on the class. Complex conjugate. These are complex vectors we're now rescaling in length. So now this is a k-dimensional vector. And in k dimensions, there can be at most k such vectors. To express things in terms of irreducible representations, we need to span the same space. Hence, this is the same k dimensions.